What if the equations were correct, but the physics was wrong? Not wrong in calculation, not wrong in prediction, wrong in what they were actually describing. That question sounds strange. It probably should. In the early 21st century, the standard position among physicists was that mathematics and physical reality were essentially the same thing. That if an equation worked, if it produced accurate predictions about measurable phenomena, then the equation was not just a tool. It was a window into the structure of the universe itself. We are looking back at this now from a distance of approximately 75 years. And what we observe is not a civilization that was foolish. What we observe is a civilization that was extremely early. A civilization that confused the power of a map for the territory it was mapping. This transmission is a retrospective analysis of a specific and consequential transition in human understanding. The period we are examining runs roughly from the 1920s through the early 2000s. It is the period during which theoretical physics became increasingly and then almost exclusively mathematical, during which abstraction became the primary mode of scientific inquiry, and during which a particular question was quietly set aside, treated as either unanswerable or unnecessary. The question was this: what is the mathematics actually made of? To understand what happened, you need to understand what physics looked like before it became fully mathematized. In the 17th and 18th centuries, natural philosophy, the discipline that would eventually become physics, was deeply committed to mechanism, to physical explanation. When Newton described gravity, he was troubled by it. He produced equations that worked with extraordinary precision, but he could not explain the mechanism. He could not say what gravity actually was, how it propagated, what it moved through. His famous phrase, hypotheses non fingo, I frame no hypotheses, was not a philosophical position. It was an admission of incompleteness, an acknowledgement that the map existed but the territory remained obscure. For roughly 2 centuries following Newton, physicists held this tension in productive balance. The mathematics was powerful, but the expectation remained that a mechanical explanation would eventually follow, that someone would find the thing underneath the equation. That expectation began to dissolve in the early 20th century, and the dissolution was not forced by failure. It was triggered by success. Quantum mechanics arrived, and it worked better than anything before it. And it came with a warning embedded in its foundations that most people chose to treat as a feature rather than problem. The warning was this: the mathematics of quantum mechanics did not describe a physical reality that existed between measurements. It described probabilities. It described what would be observed. It was silent, structurally silent, about what was actually happening when no one was looking. The Copenhagen interpretation, which became the dominant framework for understanding quantum mechanics for most of the 20th century, essentially institutionalized the silence. Do not ask what the particle is doing between measurements. The question is not meaningful. The mathematics is sufficient. That was the moment, that specific intellectual move, repeated and reinforced across decades of successful research, trained generations of physicists to accept the mathematics as the explanation rather than as a description. And then something followed from that acceptance, which was almost invisible at the time, but is quite clear now. If mathematics is the explanation, then more mathematics is better explanation. If the equations are not just describing reality, but constituting it, then the project of physics becomes a project of finding the most complete, the most elegant, the most unified mathematical structure possible. This is not an unreasonable inference. It followed logically from premises, and it produced genuine progress in the middle decades of the 20th century. The standard model of particle physics is one of the most precisely confirmed theoretical structures in the history of human science. Its predictions match experimental results to extraordinary decimal places. It is, by any measure of predictive power, a triumph. But look at what it does not tell you. It does not tell you why those particular particles exist. It does not tell you why the constants have the values they do. It does not tell you what a quantum field actually is in any physical sense. It gives you a mathematical object called a field, defined by Lagrangian, and it tells you that when you calculate correctly using this object, you get accurate numbers. It stops there. It was designed to stop there. Stopping there was treated as intellectual maturity. We are recording this now because that stopping point, which felt like the stable floor of modern physics, turned out to be a suspended platform. There's a concept in the epistemology of science called underdetermination, the idea that a given set of observations is always compatible with more than one theoretical framework. That data alone cannot uniquely determine which theory is true, only which theories are consistent. Early 21st century physics encountered underdetermination at a scale it was not prepared for, and it responded in a way that is instructive to examine. By the early 2000s, the leading candidate for a fundamental theory of physics was string theory. String theory proposed that the most basic constituent of reality were not point particles, but one-dimensional vibrating strings, existing in 10 or 11 dimensions, most of which were compactified, curled into geometries too small to observe. The mathematics of string theory was genuinely extraordinary. It was consistent in ways that competing approaches were not. It connected to gravity in a way that quantum mechanics alone had never managed, but it produced something alarming in the process, something called the landscape. The mathematics of string theory did not yield a single universe. It yielded something on the order of 10 to the power of 500 possible universes, each with different physical constants, different particles, different laws. The mathematics was so rich, so flexible, that it could accommodate almost any set of physical facts. And that, quietly, was a problem. A theory that can explain everything explains nothing in the way that matters. A map that contains all possible territories is not a map of the territory you are standing in. What happened next is what concerns us here. Not something obvious, not something measurable, but something conceptual, a gap between description and reality. This gap was difficult to define because everything still worked. Predictions remained accurate. Technologies continued to function. Progress did not stop. But beneath that progress, a question began to emerge. Not loudly, not universally, but persistently. What if the models are not incomplete in their details, but incomplete in their assumptions? This question marked the beginning of a shift, not in knowledge, but in perspective. And once that shift began, certainty started to look different. Once that shift began, the focus of inquiry changed in a subtle but decisive way. Instead of asking how to improve existing models, a different question emerged. What assumptions make these models appear complete? This was not a rejection of science. It was a refinement of how science understands itself. Because every model, no matter how accurate, is built on a set of underlying assumptions. Some are explicit, many are not, and the most influential assumptions are often the ones that remain invisible. In your time, one such assumption was deeply embedded across multiple disciplines, that observation reveals properties that exist independently of the observer, that reality has fixed attributes, and measurement simply uncovers them. This idea felt intuitive. It aligned with everyday experience. Objects appear stable. Events appear consistent. Cause leads to effect. But at deeper levels, the simplicity had already begun to dissolve. Quantum mechanics had introduced uncertainty, not as a limitation of measurement, but as a characteristic of systems themselves. You discover that particles do not have definite positions until measured, that probabilities govern outcomes, that observation is not passive, it participates. These were not speculative ideas. They were experimentally verified, repeatedly, and yet their interpretation was carefully managed, because fully embracing their implications would require redefining the relationship between observer and reality. So instead, the framework adapted. It incorporated uncertainty mathematically. It allowed for probability distributions, but it maintained a conceptual boundary. Reality exists independently. Measurement reveals it with some uncertainty. This compromise allowed science to move forward. Calculations remained stable. Predictions remained reliable. But the deeper question was left partially unanswered. Does reality exist in a fixed state before it is observed? Or does observation play a role in defining that state? In your time, this question was acknowledged, but not fully resolved. And importantly, it was not prioritized, because the existing interpretations were sufficient. They worked. And when something works, there is little pressure to rethink its foundations. This is where certainty becomes resilient. Not because it is absolute, but because it is effective. Now consider another assumption. that space and time form a stable background, a stage upon which events occur. This idea had already been challenged by relativity. You understood that time can dilate, that space can curve, that observers in different frames experience reality differently. These were profound insights. They redefined physics. But even within relativity, there remained an implicit structure, a framework within which these variations occur, a geometry, a continuity, something stable enough to support variation. This stability was necessary. Without it, prediction becomes impossible. But stability can also conceal deeper dynamics. What if space and time are not a background, but an emergent property? What if they arise from interactions rather than existing independently? At the time, such ideas were explored, but they remained at the edges because the dominant framework did not require them. It functioned without redefining the foundation. And so, once again, the question was postponed, not dismissed, but deferred. This pattern repeated across multiple domains. Energy was treated as a conserved quantity. Information had defined limits. Entropy followed predictable laws. Each of these concepts was supported by evidence, and within the observable domain, they held consistently. But consistency does not guarantee universality. It guarantees stability under certain conditions. And this is the distinction that began to matter, because as observational capabilities improved, new conditions became accessible, new scales were explored, new interactions were detected, and within these new contexts, subtle deviations appeared, not contradictions, but variations, behaviors that did not fully align with existing interpretations. At first, these were integrated into the existing framework, adjusted, refined, extended, but each extension added complexity. Each refinement introduced new assumptions, and over time, the system became more precise, but also more constrained, because every added layer depended on the previous one, and the deeper the structure became, the harder it was to question its base. This is where the major paradigm tension emerged, not between data and theory, but between stability and flexibility. The system was stable. It worked, but it was becoming less flexible, less open to reinterpretation, less responsive to fundamentally new perspectives. And this tension reached a critical point, not suddenly, but gradually, as more anomalies accumulated, as more questions remained unresolved, as more explanations required increasingly complex adjustments. At some point, a different approach became necessary, not to refine the system further, but to step outside it, to ask not how the model behaves, but why it behaves that way at all. This shift required a change in mindset, from solving problems to questioning premises, from extending knowledge to redefining its structure. And this is where one of the most significant realizations emerged, that many of the limits considered fundamental were not properties of reality itself, but properties of interaction between observer and system. This idea did not reject existing laws. It reinterpreted them. For example, the speed of light. In your framework, it was the ultimate speed limit, a boundary that nothing could exceed. And within your measurements, this was true, consistently, but the interpretation extended beyond observation. It became a statement about reality itself, that nothing can move faster than light, but what was actually observed, that within your frame of measurement, information does not propagate faster than that limit. This distinction may seem subtle, but it is critical because it shifts the meaning from an absolute constraint to a relational one, a constraint that depends on how measurement occurs and what is being measured. This does not invalidate the law. It contextualizes it, and once contextualized, it becomes open to reinterpretation. This was the beginning of the paradigm crack, not a collapse of science, but a shift in how conclusions were understood. Because if one fundamental limit can be reframed, then others can as well. And if multiple limits are contextual, then certainty itself becomes conditional. This realization did not immediately replace existing frameworks. It coexisted with them. At first, it was a perspective, an alternative interpretation. But over time, as more evidence aligned with this view, it became increasingly difficult to ignore. and eventually it became necessary to adopt because it explained more, not by adding complexity, but by redefining structure. Instead of viewing reality as a collection of fixed properties, it began to be understood as a network of relationships, stable under certain conditions, variable under others, and always dependent on context. This shift changed how science approached its own conclusions, not as final descriptions of reality, but as models that describe interaction within a defined frame, accurate, reliable, but not absolute. And once this perspective was adopted, certainty transformed from something to be achieved into something to be continuously evaluated. From this point onward, the idea of certainty itself was no longer treated as a destination. It became a state of temporary stability within an evolving system of understanding, not false, not meaningless, but contextual, bounded by conditions that were once invisible and now increasingly acknowledged. This redefinition did not reduce the value of earlier science. It elevated it, because what you achieved in the early 21st century was not imperfect knowledge. It was precise knowledge within a constrained observational horizon. And that distinction matters, because it reframes the entire history of scientific progress, not as a sequence of corrections, but as a sequence of expansions, each era working within a boundary, each boundary eventually revealing itself, and each revelation expanding the space of what can be known. In this framework, your laws of physics remain valid, but their meaning changes. They are no longer seen as final statements about reality. They are understood as stable expressions of reality under specific conditions of observation, scale, and interaction. This shift has a profound implication. It means that what you call fundamental may actually be emergent, that what appears absolute may depend on structure, and that structure may depend on relationships that are not yet fully visible within a given observational frame. This is not a contradiction of science. It is a continuation of it, because science has always advanced by redefining what it means to understand. What once seemed fixed became dynamic. What once seemed simple became layered. What once seemed final became provisional. This pattern did not end in your time. It deepened. At one point, a critical realization emerged across multiple fields simultaneously. That observation is not separate from reality. It is part of the system that defines how reality is expressed, not as distortion, but as participation. This does not mean reality is subjective. It means reality is relational, defined not only by what exists, but by how it is accessed and by the conditions under which it is observed. Once this perspective is accepted, many earlier certainties take on a different form. The speed of light, the structure of space-time, the behavior of quantum systems, all remain valid, but their interpretation shifts from absolute constraints to contextual expressions of deeper relational rules. This change does not weaken science. It expands its interpretive depth. It allows multiple layers of description to coexist, each valid within its domain, each incomplete in isolation, together forming a more flexible understanding of reality. From our current perspective in 2100, this transition marks one of the most important intellectual shifts in human history, not because it discarded previous knowledge, but because it reclassified it. What was once considered fundamental became emergent. What was once considered universal became conditional. And what was once considered certain became dependent on context. This does not lead to uncertainty in a destructive sense. It leads to a more refined form of awareness, one where knowledge is not weakened by its limits, but strengthened by its adaptability. Because once you recognize that all models operate within frames, you begin to see those frames as part of the inquiry itself, not as invisible boundaries, but as active components of understanding. This is where the idea of certainty transforms most deeply. It is no longer about reaching a final answer. It is about continuously refining the relationship between question, model, and context. And in that continuous refinement, progress becomes endless, not because answers are never reached, but because each answer reveals a deeper layer of structure, a structure that invites further exploration. There is one final implication that emerged from this shift. It challenges a belief that was deeply held in your time, That knowledge converges toward a final description of reality. Instead, what was discovered is that knowledge expands across levels of description, each level valid, each level limited, each level revealing a different aspect of the same underlying system. From this perspective, certainty is not the end point of science. It is a temporary alignment between model and context, stable enough to act upon, flexible enough to evolve, and always open to reinterpretation. This does not diminish the achievements of your era. It clarifies them. You were not wrong. You were operating at the highest level of coherence available within your observational boundaries. And within those boundaries, you achieved extraordinary precision. But those boundaries were not the edge of reality. They were the edge of access, and access expands. This is a key insight that defines a shift from early scientific certainty to post-interpretive science. Not the rejection of truth, but the recognition that truth is expressed through structure, and structure depends on perspective. As we conclude this transmission, we return to the principle that guided this analysis. Humanity was not mistaken in seeking certainty. It was simply early in understanding its nature. Certainty was never the end goal. It was a temporary phase in the evolution of interpretation. And like all phases, it served its purpose. Signal stable. Archive updated. Transmission paused.